In this video, we're going to look at Maclaurin series. Now, Maclaurin series is a way we have of writing a series as a function of x. So we can write a function such as sine x. We will see how we could write a function such as sine x as a function of x, whatever that may be. Now, there's a couple of conditions which are very important. First of all, your function f of x must be differentiable for any number of times, and also it must be the sum of a convergent power series, and we'll see what that means once we get on it. Okay, if we let this series be f of x, which is equal to a0, a1 of x, a2 x squared, plus a3 x cubed, plus a4 x to the 4, plus a5 x to the 5, and so on, then if we just put 0 into that, i.e. we put our put 0 into the f of x, so you have your f of 0, and this term, this term, this term, this term, and this term will all cancel out. So we are left with just f of 0 is equal to a0. If we then differentiate the original thing, so we differentiate the f of x, what we're going to get is f dash of x, and it is equal to, so let's just look at these. If you differentiate this, it goes to 0. If you differentiate this, it just goes to a1. If you differentiate this, it goes to 2a2. Differentiate this, sorry, that one goes to 2a2, 2a2x. This next one here would go to 3a3 x cubed, x squared, sorry, and so on. So you can see how we arrive at our f dash of x. And again, if you then put your f dash of 0 is then going to be equal to a1. All right. If we go on then and do the same idea, continue on through, same idea, you can find your f double dash of 0. F double dash of x, remember, is just f of x differentiated twice. But you can see from working through there, f double dash of 0 is 2a2, and you can write that as 2 factorial a2. Likewise, f triple dash of x is equal to this thing here. So that means your f triple dash of 0 is equal to 3. Your f triple dash of 0 is equal to 3 factorial a2. So if we put these things back into our original thing here, so for example, your a0 you're replacing with f of 0. Your a1 you're replacing with f dash of 0. Your a2 is going to be f double dash of 0 divided by 2 factorial. Your a3 is going to be f triple dash of 0 divided by 3 factorial. And then you sub those back into this original equation. This is a result that you're going to get. So the result is, I'll just highlight it here. The result is f of x is equal to f of 0 plus x, f dash of 0, plus x squared f double dash of 0 over 2 factorial, x cubed f triple dash of 0 over 3 factorial, x to the 4, f4 of 0 over 4 factorial, all the way along, and your general term, very importantly, is x to the power of n, f of n of 0 over n factorial. And that is our Maclaurin series. For CCEA mathematics or A-level mathematics, this is given to you in your formula booklet, so you don't need to learn this off. I was just showing you where it comes from. We're now going to go on and look at how we can use this to use our Maclaurin series to expand different terms. Our first example says we're going to use the Maclaurin series to find the expansion of e to the power of x. So we're going to set this up. First thing we're going to do is just say that your f of x is equal to e to the x, and then we are going to say therefore f of 0 is equal to e to the power of 0, and anything to the power of 0 we know is 1. Your f dash of x, differentiate e of x, you just get e of x. Therefore, your f dash of 0 is equal to 1, and so on. And so you can see it's just going to continue that way. So f of 0 is going to be equal to f dash of 0, is going to be equal to f double dash of 0, is going to be equal to, all the way along to f of n of 0. They are all going to be equal to just 1. So therefore, your e of x is equal to, I'm just going to write out Maclaurin series again, f of 0 plus x times f dash of 0 plus x squared times f double dash of 0 divided by 2 factorial plus x to the power of n f of n of 0 over n factorial plus dot 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 and so on and so on and so on. So when we sub in what we already know from above, we have 1 plus x plus just x squared over 2. That's what 2 factorial would have been. I'll just write it as 2 factorial actually. And then plus dot dot dot. Your general term is x to the power of n over n factorial. It's an infinite series, remember, so just do a plus dot 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 after that again. And that is all we have. And last couple of lines on this page, we'll just continue on over with this in a wee second, but we'll just say if x is equal to 1, just to show you that it does work, e to the power of 1 is equal to 1 plus 1 plus, that would be 1 over 2 plus, and so on and so on and so on. But if you put it in, 1 over n factorial, if you put that in, it would work out as 2.718218, and that's the 7 decimal places. So you can see that it does work. In this example, we have to find a logarithmic series, so we're going to let our f of x be equal to ln of 1 plus x. Okay, so your first thing you do is you write down your f of x is equal to ln of 1 plus x. And we want to say if you put in 0, so your f of 0 is going to be equal to ln of 1. Ln of 1 is just 0. Your f dash of x, and I'm just going to show you where this comes from. So in general, if y had been equal to ln of some function of x, then your dy by dx is going to be equal to f dash of x over f of x. So in this case, it's just going to be 1 over 1 plus x. And therefore, your f dash of 0 is 1 over 1 plus 0. So that's just 1 over 1, which is just 1. Before I differentiate, that's going to be awkward for me to differentiate in its current form. I'm just going to write that in index form as 1 plus x to the power of minus 1. And then again, I'll do this over here just to say how I'm doing that. If y is equal to 1 plus x to the minus 1, dy by dx would be equal to, so differentiate with respect to the power, you'll have minus 1 times 1 plus x to the minus 2. Differentiate inside the bracket, you just get 1. So it's just minus 1 times 1 plus x to the minus 2. So my f double dash of x is equal to minus of 1 plus x to the minus 2. The same idea to get to the next one, we're going to differentiate a function of a function. So f triple dash is going to be equal to positive 2 times 1 plus x. The power is now minus 3. And I'll go back and do the f of 0, the zeros of those ones. And I'll do a couple more. f4 of x then is going to be equal to minus 6, 1 plus x to the minus 4. And f5 of x is going to be equal to 24 times 1 plus x to the power of minus 5. Okay, just got to go back and do the zeros for all of those. F double dash of 0 would just be equal to minus 1. F triple dash of 0 would be equal to 2. F5 of 0 would be equal to minus 6. And F5, sorry, that was F4 of 0 was equal to minus 6. F5 of 0 is equal to 24. Okay. We're going to also write those in terms of the factorials. So I'm just making a wee bit of room for myself here. And I'm going to write those in terms of factorials. This first one is just 1. That's fine. We can't really do anything with it. The next one, f double dash is minus 1. The next one then is going to be 2, which is 2 factorial. My 6, minus 6 it is, sorry, that's minus 3 factorial. And the 24 is 4 factorial. So they're oscillating here positive and negative. So it's a very good example for us to see. We need to see how do we actually get something oscillating between positive and negative and vice versa in this. Okay, so we're just going to put a wee dot, dot, dot. Your f of n of x, first of all, your general term would be, so if we have a wee look at what we've got, 24, in the previous one, this was for our fifth differential, and it was 24, which is 4 factorial. So it's really, leave a wee gap here just for a wee second, that's going to be n minus 1. So for the nth term, it's going to be n minus 1 factorial times 1 plus x to the power of minus n. And to get the oscillating, positive and negative oscillating thing going on, we have to do minus 1 to the power of n. And again, we'll go n minus 1. So your general term, f of n of x, is equal to minus 1, n minus 1, upon n plus 1, that's a factorial, and then upon 1 plus x to the minus n. Therefore, you've got your f of n of 0 is equal to, so when you put 0 through all of that, you're just going to get minus 1 to the power of n minus 1 times n minus 1 factorial. So we're now ready to put that into our Maclaurin series. So I'll just scroll down for our Maclaurin series. So Maclaurin gives the following. So you're going to have ln of 1 plus x is equal to, and my first term is just going to be x plus x squared over 2 factorial, and my first term was minus 1, and then I've got x cubed over 3 factorial, and that's times 2, and then I've got x to the 4 over 4 factorial, and that's times minus 3 factorial, and then I've got x to the 5 over 5 factorial, and that was times 4 factorial. Do plus dot dot dot, and we'll finish this off over here. My general term then is x to the n over n factorial times minus 1 to the power of n minus 1. That's times n minus 1 factorial. And you can see what I mean. The hard part of these questions are going to be tidying up the general term. Okay, we're going to start tidying this up. So when we tidy this up, it's just going to be x. The next term is then going to be minus 1 times x squared over 2 factorial, which is just going to be minus x squared over 2 factorial, which is 2. The next term you've got, and we'll just stop here a wee second, we'll have a look at this one. So I'm looking at this term here. What you've got is x cubed times 2. That's over 3 factorial. Now 3 factorial is 1 times 2 times 3. So what happens is these two cancel out. So overall that just becomes x cubed over 3. Okay, so I'll just write that in the proper color, in the blue. And that is then going to be plus x cubed over 3. And then we'll look again in the green, we'll look at the next one. So if we look at this one, it is equal to x to the 4 times, we'll say minus, and then our 3 factorial is 1 times 2 times 3, and 4 factorial is 1 times 2 times 3 times 4. So that 1 cancels with this 1, this 2 cancels with this 2, the 3 cancels with this 2, just leaving you minus of x to the 4 over 4. Okay, so we can then tidy that up, and that just becomes then just minus of x to the 4 over 4. And the same idea with the x to the 5, 4 factorial over 5 factorial, that will just become x to the 5 over 5. And our last line, and I'll separate this out a wee bit to show this is a different, that was my first thing. It's a mess, apologies. And then we'll go on down and we'll see my general term then. Same idea. So this is us looking at our general term. The general term was x to the power of n over n factorial times minus 1 to the power of n minus 1 times n minus 1 factorial. So when you cancel, this will cancel out with this to just give you x to the n times minus 1 to the power of n minus 1 to the power of n minus 1 all over n. So that's what your general term is going to be. So we'll squeeze that one on as well. So your last term then, just say dot, 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 and then that was plus your x to the n over n, and that was times minus 1 to the power of n minus 1 plus dot, 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 because remember it is still an infinite series. We just need to say what the domain of convergence is for this thing. So the domain of convergence is a bit strange. We'll just write this in first, just say which has a domain of convergence and it's minus 1 is less than x is less than or equal to 1. Okay, and we'll say why it is. It's a less than here. I'll explain why this is, and I'll just say it can't be minus 1. And that's because ln of 0 is not defined. So that's going back to the original original function at the very start was ln of 1 plus x, but you can't have minus 1 as your x value because ln of 0 is undefined. Okay, so what it has between 1 and minus 1 and 1 is if you look at these terms, and I'll just pick one for example here. The only way this is going to converge, this whole sequence is going to converge, is, for example, this highlighted term here is getting smaller. So it's effectively, as you go along, these terms get incredibly small. And that's only going to happen if your number is between minus 1 and 1. So, for example, if you pick 0.1, which is between 1 and minus 1, if you did 0.1 squared, it gives you 0.01, so it's getting smaller. 0.1 cubed would be 0.001. 0.1 to the power of 4 would be 0.00001, and so on. So they're getting smaller and smaller and smaller. So effectively, the further you go along the sequence, the terms themselves get smaller and smaller and smaller. So they effectively go towards 0. So that's what we mean by our domain of convergence. Okay, so we will move on from this and we'll look at a slightly different way that we can do this as well. Okay, next thing we're going to do is we're going to look at a slightly different way of looking at this. Now, this is a perfectly acceptable series for this. We're just going to look at something slightly different. So we're just going to say putting minus x for x, we obtain ln of 1 minus x is equal to, and it's just going to be minus x squared over 2 minus x cubed over 3 minus x to the 4 over 4. And we're going to call this equation 1. So if we're calling this equation 2, go back and call this one up here, call this one equation 1. So we've got equation 1 now and equation 2. So if, and in this one, whose domain of convergence is, so it's slightly different than the last one. So it's minus 1 is less than minus x is less than or equal to 1. And i.e. that becomes 1 is greater than x is greater than or equal to minus 1. Or you can write that as, minus 1 is less than or equal to x is less than 1. There's other ways of looking at that as well, but whatever way you look at it, that's what you should get as your domain of convergence. So the other way of looking at it is thinking, if you think back to here, to this bit I've just highlighted, it's not going to work if you have ln of a 0. So that's why you can't, it's not allowed to be 1. X can't be 1 because 1 minus 1 would give you 0. Okay, right, now if you take those two things away from each other, so if you do equation 1 minus equation 2, what that would give, equation 1 minus equation 2 gives ln of 1 plus x minus ln of 1 minus x, which is equal to 2x plus 2x cubed over 3 plus 2x to the 5 over 5, and so on. Now, if you just think about it in very simple terms, the first two sequences, they started with the x term, then you jump to the x squared term, then they jump to the x cubed term, jump to the x fourth term. This one starts with the x term, then jumps straight to the x cubed, straight to the x to the 5, and so on. So basically, it's going up to higher powers quicker, which means it will converge an awful lot quicker. Okay, so it's actually a quicker sequence, a quicker series to use. So we tidy that on up, and using our second rule of logs, we can write the left-hand side as ln of 1 plus x over 1 minus x, and then is equal to, I'll just take a 2 outside of bracket, 2 upon x plus x cubed over 3 plus x to the 5 over 5, and I should have put a wee plus dot 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 in there, plus dot dot dot, and so on. And we'll call this equation 3, and then we will talk about equation 3. Okay, and this sequence, which has a domain of convergence minus 1 is less than x is less than 1. So really quite simply, i.e. Both series 1 and 2 are convergent. And then how do we actually use this thing? So it converges a lot quicker. We'll just say ln 2, for example, we're going to pick one. Ln 2 can be calculated. Ln 2 can be calculated using series 3. By replacing x with 1/3, and I'll show you why that is in a wee second. X with 1/3. So that means you could put ln 2 is equal to, then it would be just 2 times 1/3 plus 1/3 divided by 1/3 cubed divided by 3, which would be 1 over 81, plus it'll be 1 over 5 times 3 to the power of 5, and so on. And if you did that, it gives you approximately equal to 0.693, and we'll just say which converges more rapidly than equation 1. Which converges more rapidly than equation 1. Okay, just to show you why we actually had to put a third in to get our ln 2, let's just look at that. So we're looking at this bit here, and we're putting a third in, so that's going to be 1 plus 1/3 over 1 minus 1/3, which is going to be 1 plus 1/3 is going to be 4 over 3, and 1 minus 1/3 is going to be 2 over 3. So that's what your numerator is, that's what your denominator is. 4 over 3 divided by 2 over 3 is just 2, so that's why we put 1/3 in to this thing. So that's that explained now as well. Our last example for this video says expand cos x in ascending powers of x. So let's just get cracking on this one. Dead easy. It just says let your f of x be equal to cos x. And we'll just differentiate them all first, get a few terms, and then we'll do the zeros off them all. So f dash of x is just going to be equal to minus sine of x. F double dash of x is going to be equal to minus cos of x. F triple dash of x is equal to sine of x. f4 of x is going to be equal to just cos of x. That will do us. And then we'll just say therefore, and you'll have your f of 0 is, so cos of 0 is 1. F dash of 0, so sine of 0 is going to be 0. F double dash of 0 is going to be minus of cos of 0, which is minus 1. F triple dash of 0 is going to be 0. F4 of 0 is going to be equal to 1. So we're ready to go. We've got everything. We'll just write down our Maclaurin series again. F of x is equal to f of 0 plus x times f dash of 0 plus x squared, f double dash of 0, and that's divided by 2 factorial, plus we'll do one more, x cubed of triple dash of 0 divided by 3 factorial. And then we'll just write down our general term, which is going to be x to the power of n, f of n of 0 divided by n factorial, and so on. So if we then put our values in, we're going to have therefore cos of x is equal to f of 0, which is 1. Your f dash of 0 is 0, so we can ignore it. We're jumping on to our x squared times your f double dash of 0, which is minus 1, so it's going to be minus x squared over 2 factorial. And I'll just leave it as that, 2 factorial. And then, so that's a mess, 2 factorial. And then next term we would have would be our x to the 4 term, so plus x to the 4, and it's going to be over 4 factorial, and so on and so on and so on, until you get to your general term. And my general term, I'm going to write it as minus 1 to the power of r, because they're oscillating, but also, tricky enough one here, our power of my x is 2r. Now the reason for that is, if you look at what we've got, we're skipping and we're missing out terms as well. So your first term was 2, the next one is 4, so it's all the multiples of 2 are the powers we're going to get. So you need to have 2r, that's how we do that. Likewise, had it been multiples of 3, it would have been 3r. Had it been a multiples of 4, it would have been 4r. And then we're dividing by, and it is, so notice here, the power, if I can just highlight one here, I'll highlight my 4, x to the power of 4, and it has the same 4 factorial. So what we have on our denominator is going to be 2r factorial, and that is it. Done. Okay, and this one, it's valid for all. Valid for all values of x.